Professor Ishii, thank you very much for the very kind introduction. I couldn't understand, unfortunately, all, but some words I understood, and it is a great pleasure for me to be invited here to this HiSEP program. And already last week I gave a talk, and now in the third talk I will introduce or will give you a short introduction to a special part of inorganic chemistry. It is a so-called bioorganometallic chemistry. But before I go into detail some fundamentals of bioorganometallic chemistry, I would like to give you a short introduction to organometallic chemistry. The question is, what is organometallic chemistry? You have learned chemistry now, you have heard what are main group elements, and you have heard what are transition metal elements, and now the question is, what means organometallic chemistry? Yeah, organometallic chemistry, the definition of organometallic chemistry, that's a very important branch in inorganic chemistry, because organometallic compounds are very important systems in catalysis, in inorganic or organometallic catalysis. These are very important compounds also in nature. That is what I will show you in the second part. And organometallic compounds are also interesting from itself to produce organometallic compounds. And what are now organometallic compounds, or what is organometallic chemistry? The definition is, in the pure sense, you have a metal moiety and you have a carbon bond. So you have a ligand, that's a ligand which is coordinated via the carbon atom to a metal moiety. And the metal could be a main group metal, that means aluminium or germanium or gallium, or a transition metal. And today I will talk exclusively about transition metal organometallic chemistry. And that means you have here a transition metal with some other ligands, and you have a minimum at least one ligand which is coordinated via a carbon to the metal moiety. That is a so-called organometallic compound. And you will see these compounds are not only interesting in the sense of chemistry, but you can also find in nature, in several enzymes, systems which have a metal carbon bond, and the metal is a transition metal. Now, here are some examples, very simple examples of so-called transition metal organic or transition organometallic compounds. Here you have iron, that is a transition metal, and you have three different ligands which are bonded via a carbon atom to the iron. You have here the phenyl group, that's a phenyl, that is coordinated to the iron, bonded to the iron. You have here a so-called cyclopentadienyl. Today I will not talk about these ligands. I think about this chemistry you will hear later in later lessons next year or whatever you will learn this. And the third one, and that is very important also for today, for my lesson today, you have the CO. CO, you all know what is CO. CO is carbon monoxide. Carbon monoxide is a gas, and this gas, CO, you can coordinate to a transition metal. And these are the oldest transition metal organometallic compounds. The oldest one, these are developed, let's say, in the beginning of the last century, and one famous name is Hieber, Professor Hieber. He was chemist in Stuttgart and later at the Technical University of Munich, and he developed this chemistry of transition metal carbonyl bonding. So for today, I will just talk about the iron or the metal CO bond. Two others I will show you, but that is the most important one. Here we have also an iron complex with 4 carbon monoxides. Here we have another ligand, also coordinated via carbon to this iron. This is an ionic compound that is also a transition metal organometallic compound. These are, now you have a first impression, what are organometallic compounds. You have a metal and bond it to a carbon atom. Today, you expand it also to other elements. When you can say organometallic compounds, you can also say if a silicon or a germanium or a tin is coordinated to a transition metal, then you can also speak from organometallic chemistry. But I think in the entirety, in the special sense, iron carbon or metal carbon, metal carbonate. So now, at first, I will introduce you CO, carbon monoxide, as a ligand in transition metal complexes. Why is CO so important? CO is so important because it is first the oldest examples of organometallic compounds, as mentioned before, and there is and in the case of CO, you can explain very well the nature of bonds of the carbon to the metal. You all know the so-called Lewis structure formula. You have learned this in the first year to write a formula after Lewis structure structure models. You have electron pairs, and electron pairs are bonding one atom to the other atom. Lewis structure. And that you can also do with carbon. You have here a CO, and you can bond this to a transition metal. And you can formulate here a metal carbon bond. And now I can show you here normally, if I have a normal carbon-carbon bond, here, that is a normal carbon-carbon bond. That is maybe a ketone. So we have here a CO, R, and also a carbon-carbon bond. But now we switch to a metal. And you can write metal and CO. Now let us write the Lewis formula from CO. We have here and here a lone pair. You can write your formal charges. You can say here plus, minus, formal charges. And then you can see this CO as a kind of Lewis space. That's a Lewis space with a lone pair. And that's a Lewis acid. Please, if you have some difficulties to understanding, please interrupt me. Don't wait at the end when we discuss. If you have any question, please ask me. That's not a problem for me. So, and then you can say, that's a Lewis acid base adduct. You can say metal, that's a transition metal. Transition metal. And you can write this formula. In this case, normally you can take away the formal charges. This formula we are writing now without any charges. You say here, that is a Lewis acid base atom of metal 2CO. That is what you know. That is a very simple description of this bond. But now, you could write, and that you also know, you could write in special cases mesomeric forms. And also in this case, you can write a mesomeric form. You know mesomeric forms from olefins, maybe from benzene, these mesomeric forms. And you can write here this kind of mesomeric form. That is possible. You take an electron here from the metal, have here some electrons from the metal, right here and here. So this is a kind of mesomeric form, as you know it from normal organic or inorganic molecules. But that is not right. I think you can write this, but in the sense of a modern understanding of bonding in organometallic chemistry, that is not the best description. You can write it, but it is not the best description. It is better you do it following. First, I will explain you why it's not the best one. You know, normally in main group elements, you have the responsible orbitals sigma S and P with 1 S and 3 P orbitals, depending on the main number. But when you come to the transition metals, then you have additional 5 d orbitals. You have 1 S, 3 P, and 5 d orbitals. And that is important now. That is a difference to the main group chemistry. In the main group, elemental d orbitals don't play a special role. But in the transition metals, there the d orbitals are extremely or very important. And you already know from tests before, that there are 5 transition metals, 5 d orbitals depicted here. We have here a coordination system X, Y, Z, and depending of this orientation, you have 3 orbitals located here between the axes, the d orbital X, Y, X, Z, X, Y, X, Z, Y, Z, and you have these orbitals located along the axis, X square minus Y square and Z square. These are the 5 d orbitals in transition metals. And now you can describe this bonding in a different way. And that is written here. You can write this description, the pure Lewis acid base atom, by this interaction. You have the Z square orbital, which can interact with this lone pair by an overlap, and this orbital, this CO orbital, is filled 2 electrons, and the 2 electrons can be interact with this empty Z square orbital from the metal. So we have the MCO sigma donor bond, because the symmetry is sigma. That is exactly, or not exactly, but that is comparable with this description. We have here the sigma bond. Here 2 electrons, and here an empty orbital. We have an interaction, and we have the formation of a sigma orbital. That is the most important contribution for the bonding. But then, and that is the reason why I have explained you that transition metals have d orbitals. Because electron density, which is located at the metal moiety, can be transferred via a filled d orbital, maybe XZ or YZ, into an empty pi star orbital of CO. That I can explain you. We have this orbital, which is filled, lone pair, that can act as a donor to the empty. To the empty dz square orbital, and on the other hand, here we'll take this filled d orbital and the pi star orbital of CO. That is a pi star orbital of the CO. You have learned this already in the case of olefins. Normal olefin, ethylene maybe has a pi orbital filled and a pi star antibonding. That is a p star, that means antibonding orbital. So, and here that is filled, maybe dxz, and that is empty. So, and now electron density from the metal moiety can be transferred back to the empty pi star orbital of the CO. And that is a difference to main group elements. In the case of main group elements, you cannot formulate this description. That is specialty for transition metals. So you have an MCO sigma donor bond, and on the other hand, you have an MCO back donation. That means back donation, electron density. That means not that electrons were transferred. No, just electron density. That's a difference. That makes a difference. Electron density is transferred back to the pi star, the empty pi star orbital of the CO. And that is the so-called MCO back donation. That's a p acceptor. So you can describe a transition metal CO bond as a sigma donor and a pi acceptor bond. So that is, in my opinion, the most important fundamentals you have to learn in transition organometallic chemistry. The understanding that we have here these two types of bonding. The most important, the main contribution is delivered by this description, but also this contribution is very important for the understanding of the bonding. And if you compare it now with the so-called old description, with the Lewis description, you can see that is more representative. The sigma donor bond, and this one is more representative by the p acceptor bond. So that is main metal carbon ligand to a transition metal. Okay, you can transfer this model, this old, this Chet-Dankerson model. Sorry, Chet-Dankerson model by chemist Chet. That's Chet was a famous chemist from England in the middle of the last century. He developed many things in organometallic chemistry, and mainly Czech is the so-called father of this description. This description was established in the 60s of last century, and today you can read it still in every teaching book. So now you can transfer this jet model also to other ligands. And I will show you two other ligands which are also interesting for the understanding of organometallic chemistry as well as for the bioorganometallic chemistry. I will talk a bit later. The next ligand is olefin. Also olefins can be described in a similar way. But now you have not an olefin coordinated in this way, that you have metal CO on one axis. That is a different. In this case, you have an olefin perpendicular to the metal compound or to the metal moiety. But it's very similar. You have here the so-called Lewis description. You have here the pi bond of the olefin, and here between the two carbons is a higher electron density. And so the olefin can act as a donor. So electron density from this double bond system, from this P system, can be transferred to empty orbitals of metal. Very similar to here, when you have electron density transferred from the CO to the empty dz square. And you can write also, as here, in a mesomeric form, you can say, okay, we don't write it in this olefinic form, but you can write a so-called metallocyclopropane. A metallocyclopropane, you know, a three-membered ring is called cyclopropane, and if you substitute one carbon by a metal, you say it is a metallocyclopropane. And these olefins could be a normal, it could be ethylene, or this could be these olefins. All these olefins you can call it. But now, in the modern description of this bond is depicted here. We have again an empty dz square orbital, exactly here in the case of the carbonyl bond. And this empty orbital can accept electron density from the pi system of the olefin. That is a filled bonding pi MO molecular orbital from ethylene. That is here. No. The ethylene, and you can describe it in the MO description. Maybe MO scheme, energy, two orbitals, two molecular orbitals, and that is a pi orbital, and that's a pi star orbital, and the pi orbital is filled with two electrons. That is bonding, that is antibonding. So that is the description of a ethene. And now you can take this and you describe an interaction of the, sorry for this, that you always have to switch on and switch off, sorry. And you can describe this as an interaction of this filled pi orbital, the bonding orbital, with the empty dz square orbital. So we have, say, M olefin sigma donor bond. And compared to the CO bonding, we can also formulate a back bonding system, or a back bonding part. Here you have again a filled dxz or yz orbital, and that can interact now with the pi star orbital. It's an antibonding. Here, the antibonding orbital that is empty, as you can see here, it's empty, so it can accept electron density. And the metal transfers electron density from itself to the pi star antibonding orbital. So we have again a metal olefin sigma donor bond and a metal olefin pi back donation, the so-called pi acceptor bond. With, so again, the sigma donor pi acceptor bond. So you can describe bonding of olefin to magnets. Now we have learned two important ligands in organometallic chemistry. The CO, that is bonded here along this X and CO. And then the olefins, that is now that is an example for all other olefins. Every olefin is correlating in this sense to the metal. So it is enough to explain it in the case of ethylene. And in this case, we have a perpendicular orientation of the olefin to this axis here. But in principle, you have the same sigma donor P acceptor interaction. So that is now the olefin. And the third ligand, what we need also for understanding for bioorganometallic chemistry, is the so-called hydride. Hydride is ligand in transition metal complexes. Now, what are so-called hydrides? You know hydrides also from the fundamental lesson. We have hydrogen. Hydrogen is gas, and you can cut this molecule either in two atoms, a homolytic cleavage, it's a homolytic, so you get two atoms, or you can formally cleave it in H plus and H minus. That's a formal description. That is just, it's possible. This reaction is not so easy, that we will see why it's not so easy. Yeah, why it's not so easy, because the bond energy is around 104 kilocalorie per mole, or around 420 kilojoule. I think we work sometimes with kilocalorie. I don't know, are you working only with joule or also with calorie? Joule, okay. But then you have to multiply this with 4, so around 420 kilojoule. And the bond is relatively strong. The H bond is relatively strong. I remember this because it's kilocalorie, very easy to remember, because you say HH bond, it's around 100 kilocalorie. That is so you can remember very, very easily. But also in kilojoule, it's a fourfold, so around 420, 430 kilojoule per mole. It's a relatively strong bond, the HH bond. And you need energy to cleave it, and we will see how is this done in nature. So, but formally you can cleave this in a proton. Yeah, okay, in H plus and H minus. That is a proton. Proton, like you know, as you know from protein acids. If you dissolve hydrogen chloride in water, you get H3O plus and Cl minus. Cl minus, that means you have a proton. And the other one, the H minus, that is a hydride. A hydride is, so you can say the proton is the oxidized hydrogen and the hydride is a reduced hydrogen. This has 2 electrons. A hydride has 2 electrons. Yes, hydrides, maybe you know from the fundamental lessons, hydride you can form with alkali metals or earth alkali metals. Maybe you know lithium hydride, sodium hydride, potassium hydride. You know all the salts. If you dissolve these salts in water, then you get hydrogen and a base. Okay, that are hydrides. And now we were interested in hydrides. Hydride, you can write it here, hydride is also, now I have to write it differently, but so. I have to write it here as a sigma orbital, and the sigma orbital is filled with 2 electrons. So this anion can also act as a donor, ion which transfers electron density to metal, transition metal complexes. I can show you this here. These are some examples. We have here metal. This metal could be main group or transition metal. Main group hydrides could be ionic forms. That means you have a ionic, you have a lithium cation and a hydride anion. Or in the case of alumina, you have not an ionic bond, you have a polarized bond between alumina and hydride. You have a bond alumina hydride. And in the case of transition metals, we have always here this bond, a metal H bond, metal hydride bond. That means a hydride is bonded to the metal. And hydrides could be coordinated in different ways. Here you have one hydride coordinated to a metal moiety, or a hydride is kept 2 metal moieties, or 3 metal moieties, or even it could be included in a so-called cluster system. Cluster system means these are 6 metals are forming a so-called cluster, and inside is a hydride. That is not so important for today, just that you can see it. The important one is this one, the metal H. So how can we explain this one? When we have here An, and we have 2 hydrides. We can call it one hydride or 2 hydrides. These are hydrides. Hydride giving electron density to an empty orbital of metal. And how can we explain the formation of this compound? You take a metal moiety and you can react this with H2, with dihydrogen, with the gas, with the element. And in special cases, not in every case, but in special cases, if you bring this H2 molecule very close to the metal moiety, then one can observe the interaction of this metal moiety with H2. So you can say we have metal and the interaction between this metal moiety. So we have a metal complex containing H2 hydrogen as a ligand. That is possible. Not in every case, in every transition metal complex, but that would be too far today. That is for more advanced lessons. But today, I can tell you, in special cases, we have this form of hydrogen bonding, or dihydrogen bond to a metal moiety. And how can we describe this? And again, sigma donor, p acceptor bond, the hydrogen, that is a sigma orbital. If you have H2, you can form two orbitals, the sigma, the bonding, and the sigma star, the antibonding. And the sigma bond, the sigma orbital is filled with 2 electrons, the antibonding is empty. And here you can also formulate an interaction between the sigma MO of H2 with the empty d z square orbital, leading to this kind of interaction, and then again a back bonding of filled d orbital of the metal to the empty sigma star orbital of hydrogen. And so you have explained, or you can describe the interaction of hydrogen, of the dihydrogen of the element to metal. And when the interaction of the dihydrogen with the metal is very strong, then the hydrogen-hydrogen bond will be cleaved with a cleavage, and you get finally here the hydride. In some cases, there are equilibriums between this one, the H2 bonded complex, with the dihydride complex, with the cleavage, with the cleaved, or with the cleavage of the HH bond. That is, in some cases, can be observed. So that is the way to get hydrides. It's one way, not all way, but one way to get hydrides. Now, I have shown you 3 important ligands in organometallic chemistry that are really the fundamentals of organometallic chemistry. I have shown you the bond of CO, the carbon monoxide, to a transition metal, sigma donor, pi acceptor bond. I have shown you the coordination of an olefin. Olefin, now perpendicular to the metal axis, also sigma donor via the pi orbital with the empty orbitals of the metal, and the pi back bonding in pi star orbitals of the olefin. That is the second important ligand. And the third one are the so-called hydrides. Hydride H-, and you can form hydrides of the metal by reacting of metal complexes with dihydrogen. Also by cleavage, or by cleavage, in this case by cleavage of the hydrogen-hydrogen bond, then you come here to a metal hydride. These are the most important ligands in organometallic chemistry. Please, I repeat, if you have any questions, please ask me. Don't hesitate to ask me if you have any questions. Now, let us go back to to the metal carbonyl complexes, the first examples, because here I have to introduce some important reactions. So, you have here a molybdenum complex with 6 coordinated CO ligands. So it's a very simple organometallic compound, a very old organometallic compound that was synthesized already in the beginning of the last century. The preparation is not very easy. You cannot prepare it taking molybdenum metal and CO gas, carbon monoxide gas in a tube or vessel. That is not so easy. You have to reduce, mainly you can reduce molybdenum salt to molybdenum zero, and this is under high pressure and high temperature. You can do it this just in an autoclave system. You cannot do it in a normal system. Just a few metal carbonyls can be synthesized by just reacting of metal plus CO. That's in the case of nickel. Maybe you have heard it in your first year, the so-called MOND reactions. It means nickel plus CO leads to nickel carbonyl. In all other cases, in preparation you have to use high pressure and high temperature in so-called autoclave under pressure autoclavic systems. Okay, then you have this molybdenum carbonyl. That's a very stable compound. It is a colorless crystalline compound. It is toxic because there is CO inside, and also when it's decomposite, then a very fine metal powder will be produced that is not good for the organism. So you have to be careful with this compound, but it is more or less stable. It is a stable compound. You can use it in air and so on. Okay, but the reaction with these organometallic compounds you have to carry out under nitrogen or under argon. Because in solution, these complexes are oftentimes air sensitive and moisture sensitive. Okay, you have this molybdenum hexacarbonyl. Hexa has 6, it's a Greek name of 6 hexacarbonyl, 6 ligands. You dissolve it in THF, that is tetrahydrofurane, and then you irradiate this solution with UV light, and then you can substitute one or more CO carbon monoxide ligands. The problem is to monitor, to record exactly the substitution of one CO, but that is possible because CO is a gas. You can fill the gas and you can measure the volume of the gas which is substituted, and then you can calculate if you have used 1 millimole of the starting material, then you stop the reaction when you have exactly substituted 1 millimole of CO. So then you can stop it. Then you know, okay, 1 CO ligand is eliminated from this complex. So then you have PHF coordinated to the model, and PHF is a very, very weak ligand. It's a very weak bond between this oxygen to model, much weaker than the coordination of the carbon monoxide. So you can substitute this THF very easily by another ligand. Maybe that is a so-called phosphate. Or you can do it also by amines. You can use ammonia, you can use NH3 or 3-methylamine, and you can substitute this THF very easily, and then we have this mixed compound with 5 carbonyl, and in this case 1 triphenyl phosphate. So that is a general description here. You have a metal carbonyl. N means you have a special a number of CO ligands. You eliminate one CO, and then you can add additional ligand, and you have here this compound here, or you can add again a CO in, then you have the starting material. That's interesting, yeah. Then you have the starting material. Okay, that is also a fundamental reaction in the organometallic chemistry. It's a substitution of one CO in transition metal carbonyl complexes. Another important reaction of cholinetic CO is so-called insertion reaction. Insertion reaction, that is now very important in organometallic chemistry, in catalysis, and also in the bioorganometallic chemistry, in special enzyme reactions I will show you later. But this reaction, the CO insertion reaction, you can find in many catalytic or catalyst-mediated organometallic reactions. You will learn this later also in more advanced courses, but today I will show you because the principle, in principle, it is not difficult to understand. You have here manganese complex with 5 carbonyls, and you have here additional 1 coordinated methyl group. That is also a very easy, very simple complex, very simple ligand. The methyl, you have here this we can compare it with the hydride. We have here, not the metal hydride. That's the simplest ligand. The simplest ligand. And you can write this one. Here you have the hydride. And here you have a methyl group. Yeah, it is. I think now it's good. Yeah, but I hope you can understand me. I'll put this in the microphone for 1 minute. We have here the hydride here, we have the methyl group. It's very similar. You have a methyl group, or thank you very much. Or you have a hydride, or you have a methyl group. And in this case, you have metal with this with manganese and with this 5 carbonyl ligands and 1 methyl group. And here in the hydride, you have following polarization: minus, plus, also here minus, plus. That's a polarization of the bond. We have more a methyl, a kind of methyl Ni. It's not a methyl Ni, but the methyl here is more nucleophilic. It's more nucleophilic. So, and now you react this compound with CO. And the CO, you can write here. You can draw a mesomeric form. this is a mesomeric form. This one, or you can, yeah, that is, that's great. Thank you very much. Can I show it the audience? Yeah. This is molybdenum carbonyl. This is colorless crystals. The compound shown here. This one. It's a solid, is a crystalline solid. You can take it very easily from this flask and ignite and okay. Thank you very much for this. Okay. Here you can write that in this way. And now you can see we have here delta. Here we have minus plus, but in this case, you see here is a electron sextet. Just 3 electron pairs. It means an electron sextet. So it can react with a nucleophile. But normally, carbon monoxide, when you have carbon monoxide just in a pure form, and you will react it with a nucleophile, that is very important for reaction later, with a nucleophile, that means CO plus OH minus, or with a lithium methyl, then you cannot observe a reaction. It is too inert. It is, CO is kinetically inert. But when you coordinate it to a metal, then this metal, Ni, can react with the CO, and you get this ligand, so-called acyl, the acyl ligand. You can see it is a formal addition of a methyl to a CO. And the mechanism is shown here. We have a coordinated CO. We have here the methyl. The methyl is negatively charged. The carbon here, and that's important, this carbon bonded to the metal is positively charged. So we have negatively charged, positively charged, and then the metal can be transferred to this carbon. You get an intermediate, and finally you get this so-called insertion reaction. The product looks like as when CO is inserted into the metal group, or the metal bond. But that is not right. It is not an insertion of CO in the metal bond, but the methyl group, the negatively charged or polarized, I would like to say polarized, the negatively polarized methyl group attacks the positively polarized carbon, and we have an attack in this form. The product looks like an insertion, but that is the mechanism. So we can say the coordination of CO, of carbon monoxide, to a metal makes this carbon more electrophilic, and therefore it can be attacked easily by a nucleophile. And that is a nucleophile, the metal, that's the electrophilic part. And now you have the nucleophile attacks the electrophile here, leading to this compound. That is an extremely important reaction in organometallic chemistry. The activation of carbon monoxide by a transition metal, and then the carbon is open for a nucleophilic attack, activated for a nucleophilic attack. Yeah, and this reaction you can observe also in this very important reaction. You all know, maybe also from your fundamental lessons in chemistry, you know the so-called water-gas shift reaction. What is a water-gas shift reaction? The water-gas shift reaction is depicted here. We have carbon monoxide, and this reacts under pressure and high temperature to carbon dioxide and hydrogen. Or, because it's an equilibrium, CO2 reacts with hydrogen, leading to carbon monoxide and water. That is a so-called water-gas shift reaction, which is important in industry, in industrial processes, in the preparation of hydrogen, that you can find in several industrial processes. So, the water-gas shift reaction. In this water-gas shift reaction, this runs just at high pressure and high temperature, can be catalyzed, activated, catalyzed with transition metal compounds. And that is the so-called Hieber-base reaction. That is, oh, that I have forgotten to write. That is the so-called Hieber-base reaction. You can write it here. Hieber was this pioneer, I mentioned his name already before. Hieber was the pioneer on the field of organometallic chemistry, of the modern organometallic chemistry. He was at the Technical University of Munich in the last century. He passed 1976, and he was really one of the most important pioneers in organometallic chemistry in Europe. And from this chemistry came most stimulation of organometallic chemistry in other parts, and also in the US, America, and so on. He was really one of the pioneers of this chemistry, and one of his PhD students, that was Ernst Otto Fischer. He was also from the Technical University of Munich, and he was awarded with the Nobel Prize with Geoffrey Wilkinson from the Imperial College in London, 1973, also for chemistry of carbon monoxide. But that is, you will learn it also in advanced lessons. But I would say he was really a pioneer, and he observed this reaction, or he observed that you can catalyze this water-gas shift reaction by transition metal. That's a transition metal mediated water-gas shift reaction. Or here's missing metal, transition metal mediated water-gas shift reaction. Here you have the proto reaction. CO plus water leads to CO2, carbon dioxide, and hydrogen. How can you now explain the transition metal mediated form? You start here, carbon monoxide, and you have a metal complex, you get a metal carbonyl complex. Now you know all what is a metal carbonyl complex. You know this. Then we have water, or water is also in equilibrium with OH minus. OH minus, the hydroxide, as a hydroxide. Hydroxide is in equilibrium with water. And now hydroxide, OH minus, attacks here at the positively polarized carbon. That is what I have shown you in the slide before. This carbon is now electrophilic. It's positively polarized and can be attacked by OH minus, which is in equilibrium with water. This is so-called self-dissociation of water. You can use directly sodium hydroxide solution or a carbonate, you need a bit higher concentration of OH minus. But in principle, water should be enough, but a little bit higher pH. So now the carbon is activated by the metal. Here you have the attack of OH minus to the carbon. You get CO2, you can see here now, you have O, the oxygen, the O attacks here the carbon. You can here form CO2. You can eliminate it now, carbon dioxide, that is written here. And you get metal hydride. You have also learned what is a metal hydride. Metal hydride I have shown you here. Metal hydride. And this metal hydride now reacts with water because there are protons. Water, you have the self-dissociation of water, or the autoprotolysis of water. Autoprotolysis of water. Autoprotolysis. Autoprotolysis of water. So water can react with this transition metal hydride, leading to hydrogen. And now you have again the N+. The N+ reacts with CO, and you have the so-called catalytic side. That is a very simple catalytic or a transition-mediated catalytic reaction. I think that is one of the simplest one. And I think I can teach this today even if you are in the first year, but I think all, or in principle, you have learned all these types of reaction. You know what is the water-shift reaction, you know now what is a metal carbonyl, I've taught you what is a metal hydride, and so you can explain this reaction. And this reaction now is running at lower temperature, at normal pressure, and that is an example how to use metal carbonyls as catalysts to enhance the velocity of the reaction. This catalyst is influencing the kinetic of reaction, not the thermodynamic. The kinetic catalyst is affecting the kinetic or the kinetic of a reaction. And you have also learned the difference between thermodynamic and kinetic. Thermodynamic means which energy is transferred, and kinetic of reaction means the velocity, how fast reaction is, and the catalyst is just influencing the kinetic, not the thermodynamic. That's very important. Okay, that was now the first part of my lesson. Some fundamental principles of organometallic chemistry. In the next 30 minutes, I will give you very shortly, but I think we can use now that what we learned to bioorganometallic principles. But before, I would like to ask you, are there any questions? Okay, if it's not the case at the moment, we can. I would like to talk with you later. So now we come to the so-called bioorganometallic chemistry. And now this part could be a bit more difficult, and I apologize, and please interrupt me immediately if you have some questions or some difficult to understand me. That is now a little bit more difficult than what I've shown you before. But in principle, we use now this reaction I have shown you before in nature. And nature is very smart. You know, nature is very smart. And nature is not making a difference between main group chemistry and transition metal chemistry and physical chemistry, organic chemistry. I think nature uses chemistry as it is, as chemistry. And you can learn so many things from reaction running in nature for chemistry. I think you say, okay, this reaction I have learned now in organic chemistry. Oh, I find this in biochemistry. Or I have learned this in inorganic chemistry. I can also find this in biochemistry. And that is also the case, and therefore also the name, Bioorganometallic chemistry. That means organometallic compounds in nature. Please remember the first slide I've shown you, organometallic compound, metal, carbon. And then you will find here again. And there are some enzymes, very important enzymes. One enzyme I will show you very quickly is the so-called hydrogenases. The hydrogenases are catalyzing this equilibrium, no, not this one here, but you remember I have written here the equilibrium or the reaction. Hydrogen is dissociated in hydride and proton. Here, hydrogen is dissociated in hydride and proton. Or hydrogen is oxidized to protons and to electrons which were removed. Very simple reaction, but which are very important in some organisms. You can oxidize hydrogen, you can reduce hydrogen with enzymes. And we will see the active center contains a transition metal. Then this reaction you know now very well. What is this reaction? That is the reaction I have shown 2 slides before. That's exactly the water-gas shift reaction. The water-gas shift reaction is also a very important reaction in nature, in organisms. This is catalyzed by a special catalyst in nature called enzyme. It is so-called carbon monoxide dehydrogenase. In this case, we have the hydrogenase. It's the name of the enzyme. Then we have the reaction that we have carbon monoxide, you have a methyl, a methylene, and you get here this group, methylene CO, where we have found this reaction, in the insertion reaction of molybdenum, methyl pentacarbonyl, and CO. There we have observed exactly this reaction, the so-called CO insertion reaction. That is a biological variant of the CO insertion. And finally, we have so-called nitrogenase. That is a new but very important reaction. That is the activation of nitrogen to ammonia. That is a different example, but very important. Maybe I have time or not. But these 4 examples, these 3 examples, or the type of this reaction, I have shown you before already when I told you the fundamentals of organometallic chemistry. Now let us show what are now these enzymes, and please don't be astonished about the complicated structures now, but these structures are not so complicated. These hydrogenases are active center of a special enzyme in an organism. And the most important thing is that we have here an organometallic compound. And a type of organometallic compound I have shown you before. We have again a transition metal. You remember the first or second slide I have shown you was also an iron complex. An iron complex with carbon monoxide. And exactly this type of complex you find in an organism. It's a real organometallic compound. Transition metal, CO, okay, and then is here cyanide is additionally in here sometimes. That's not so important, but important is you find a transition organometallic compound. And now these so-called iron-iron hydrogenase is activating hydrogen. And I would like to focus you just on this formula or principle to this formula. You have here the iron-iron and the carbonyl are not depicted, but you have the mention here are carbonyls. And you have hydrogen. And here you can see that hydrogen has been oxidized to proton. Hydrogen will be uptaken. You get iron hydride. Iron hydride here, metal hydride. You find it also in nature, a metal hydride. And then you release here a proton and an electron. And then a second one. So you can activate hydrogen, or you can oxidize hydrogen to protons via a metal hydride system. And these reactions are equilibriums. That means you they are also not only able to uptake hydrogen, they can also reduce protons to hydrogen. So either the oxidation, hydrogen to protons, or the reduction of protons to hydrogen. And in all cases, because these are equilibriums, you have the formation of an iron hydride bond. That's what I've shown you and what you learn in organometallic chemistry. That is very important. The activation or the production of hydrogen in nature from protons are running via a metal hydride system. More it is not necessary to explain you at that stage. I will just show you that reaction you learn in the textbook in organometallic, you can also find again in nature or in living natures, also inorganic chemistry is nature. Okay, the next two enzymes are the CO, the carbon monoxide dihydrogenase, and the so-called acetyl-ACoA synthase. I will explain to you what this means, but first let's go to the CO dehydrogenase. The CO dehydrogenase is catalyzing the Hieber-base reaction. We have learned the water-gas shift reaction. We have learned that the water-gas shift reaction can catalyzed by a metal carbonyl shown by Hieber, and exactly the same reaction is running in nature. We have here iron and nickel. Just focus your view to this unit. We have here nickel, it's a transition metal, and we have coordinated carbonyl, metal carbonyl. And you have here iron OH. And what we have learned that the carbon here, when it's coordinated to a transition metal, it is positively polarized. It's electrophilic center. And the OH is a nucleophilic particle. And so the OH can attack here at the carbon. Exactly that's what I've shown you in the case of the Hieber-base reaction. For this reason, I have here again the Hieber-base, here the water-gas shift reaction, CO water, CO2 hydrogen, here the Hieber-base reaction with the activation of the CO and the attack of OH, the elimination of CO2 and the production of hydrogen, and then again the recycling. And the same you can find here in this carbon monoxide dehydrogenase. We have here the nickel CO, and the nickel CO or the carbon will be attacked here. Also, these are equilibrium reactions. OH is attacking here to CO, leading to this one, elimination of C2, and then have again here formally the production of hydrogen, and then you have the catalytic or the enzymatic cycle. You can see water-gas shift reaction. Then in the laboratory you can simulate this by Hieber reaction, and that is reaction shown in some organisms. That is a CO dehydrogenase. Also simple organometallic chemistry in nature. And the third one is the so-called Acetyl-ACoA synthase. That is a very important enzyme because it is forming the so-called active acetic acid. I don't know if you heard this maybe in high school or now just at university, but that is a so-called active acetic acid. The active acetic acid is very important in the metabolism for the formation of lipids, for fatty acids and for lipids and for the formation of cell membranes, just as a short explanation. So this compound is very important in all in organisms for this biosynthesis. How does nature work? You have again a transition metal complex in the active center of this enzyme. You have nickel, you have two nickel atoms coordinated by special ligand. That is not so important now, but one ligand is important, and that is CO. CO is introduced here. Where is CO coming from? CO, let us go back. CO is coming from this reaction. This is old dehydrogenase is producing CO from CO2 because that is an equilibrium reaction. CO comes from CO2 from this enzyme. And now you have CO. And the CO is coordinating to one of these two nickel atoms. You have a nickel carbonyl reaction. Then you have a transfer. Nature can transfer methyl groups, CH3 groups. Methyl groups can transfer also to the nickel metal. So you have on one nickel, you have one CO and one methyl group. Please remember the reaction I've shown before with the molybdenum, the so-called CO insertion reaction. Now we have CO, we have the methyl group. The carbon again, remember this please, is positively polarized, can be attacked by this negatively polarized BH3 group, and you get exactly that what we find as product in the so-called CO insertion reaction. We have this so-called acyl group. And now there's coming a thiol from other different this pathway, and that is now substituting. You have now a substitution reaction, and you have the formation of this derivative of acetic acid. That is the formation of the active acetic acid by the so-called CO insertion reactions. Now I've shown you all three fundamental organometallic reactions: the formation of hydrides, the insertion reaction, and the Hieber-base reaction. You can find again in nature, in special organisms. And that is what I wanted to show you today. That chemistry is not just that what you are learning, what you are doing in the laboratory, and you cannot see this separated from nature. This reaction you can also find in metabolism in here in these biochemical reactions. And now I think I have 10 minutes. 10 minutes. I think that is also important. That is the next enzyme. That is a little bit far away from that what I have shown you before. That is not more a typical organometallic reaction. But I think, nevertheless, it is an important reaction, and I think the title of my lecture, it's activation of small molecules. What are the small molecules? The small molecule was hydrogen. The small molecules were CO and CO2. And now the fourth small molecule is nitrogen. And you all know how important is the activation of nitrogen. Nitrogen has a triple bond. You know this from the first course, chemistry. Nitrogen is kinetically inert. It's thermodynamically stable. It is yeah, I think it's the strongest bond you find in chemistry, in molecules. This triple bond is extremely strong. And the question is how one can activate this triple bond. And that is important because chemistry with nitrogen you can just do when you have activated it. And nature is doing this. There are special blends, you will see this, there are special blends which are able to activate this very stable molecule, and that at room temperature and normal pressure. You can see the blue direction here, nitrogen, and that is reduced to ammonia. That is what is done in nature. And the active center of this enzyme is depicted here. I will not explain it in detail. That is not necessary. It is just what I will show you again, transition methods here inside. And where can you find these enzymes which are able to activate nitrogen in this very mild way? You can find these enzymes in bacteria, the so-called nitrogen fixation bacteria, which are living maybe at this plants. You know this plant, this leukemia, and this leukemia, and here you see the roots, and at the roots here are some, yeah, these small sticks, and these small sticks, these are bacteria which is in symbiosis with this plant, and the enzyme in this bacteria is this so-called nitrogenase. That is the enzyme which is able to activate nitrogen. Okay, and these plants, or in symbiosis with this bacteria, are producing ammonia, starting from nitrogen from our air. And these plants need this for fertilization. And I think you all know nitrogen or ammonia is very, very important for fertilization. Yeah. How can we produce ammonia? And that you have also learned by the Haber-Bosch process. You have learned this in one of the first lectures. The Haber-Bosch process, that's an industrial process, which is also, in this process is also nitrogen activate to ammonia. Plants or bacteria are doing this at normal temperature, room temperature, and normal pressure. But we, or that means you being in the industry, need high temperature and very high pressure. But and the activation, the catalytic activation of nitrogen was invented around 100 years ago, a bit more than 100 years ago, by two famous persons, Haber and Bosch. Fritz Haber from Berlin and Karl Bosch from the BASF, this famous company in Germany. These two chemists was awarded with the Nobel Prize 1919 and 1931. These two persons developed the extremely important Haber-Bosch process because this process allows the transformation of the absolutely unreactive nitrogen, or absolutely the very unreactive nitrogen to the biologically applicable nitrogen, ammonia. Sorry, the nitrogen is transformed to ammonia, and ammonia can be used for reactions and for the preparation of fertilization. How is the reaction in this process? Nitrogen and hydrogen is used. Here again, the water gas shift reaction. I've shown you why the water gas shift reaction is so important. It's important because you can produce hydrogen from carbon monoxide and water. So now you have nitrogen and hydrogen. And that is the Brutto reaction. Nitrogen and hydrogen leads to ammonia. That is the catalytic reaction of nitrogen, iron is a catalyst. You need a catalyst for this reaction. Without catalyst, the kinetic of this reaction is extremely not fast, the opposite of not fast, that's langsam.
Slow?
Slow, sorry, very slow. It's very slow, thank you, right? It's very slow. It's a very slow reaction. And you can catalyze the reaction by iron as catalyst. And high pressure and high temperature. And now you can see the difference between the natural procedure from the enzyme and the catalytic reaction in industry. You all maybe know this diagram because this reaction is exothermic. It's an exothermic reaction. It means there's an energy releasing reaction. It is kinetically very slow, but it's exothermic. But you have to overcome the high activation barrier, of this N2 molecule. And that you can do either with high pressure and high temperature. But the problem is if you use high temperature and you have an exothermic reaction, then you have a decomposition of the formed ammonia. So the best is you work at high pressure and low temperature. But that's not so easy. Therefore, normally it's working, this process is working at 200 bars and 500 centigrades. Relatively extreme conditions. And that is done in these reactors. And the mechanism of this reaction was elucidated by another German chemist, by Gerhard Ertl. He was one of the succeeders of Haber. He's just working first in Munich and then in Berlin, and he was also awarded by the Nobel Prize, and he elucidated the mechanism of the activation of nitrogen on an iron, with an iron catalyst. And that is relatively complicated. I will not explain it in detail, but what I can say, first we have activated the hydrogen, 2 hydrogen atoms, and nitrogen we will also keep, and the cleavage of nitrogen that proceeds on the surface of iron. So we have a catalytic reaction, but the catalytic reaction is just running 500 centigrade and 200 bar pressure. Yeah, and nature is doing this at room temperature, at normal pressure, with this enzyme I've shown you before. Here, this is called nitrogenase, and the active center, the catalyst. The catalyst is how Bosch process is iron. And the catalyst here in the nitrogenase is this compound, iron sulfur. And this structure, or this active center, and this protein, this enzyme, allows that the nitrogen can be activated at room temperature and normal pressure. That is what I would like to show you here. That's mechanism that is not so important now, the mechanism, but the mechanism is not elucidated up to now. It is not known exactly how is the mechanism done in nature. That is still a problem, and when somebody will resolve or will find a solution of this mechanism, then there should be a new Nobel Prize. Now I'm at the end. Yeah. Okay, so now I'm at the end. Yeah, that was the last slide. I would thank you very much.
For your very interesting and fundamental lecture. I expect all students understood your lecture. 次の講義があるということで、そうなんですよ。想定外。
次の授業は岸本先生ですね。長野さん、写真を撮っていただきます。じゃあちょっと時間がないんで皆さん前の方に集まってそれで写真を撮って終わりにしたいと思いますので。